Hello, I'm Erik Dovgan, and I will present the optimization of traveling time and fuel consumption in human driving models. I will start the problem description, then I will present how the driving was simulated. Next, I will present the algorithm that we implemented, that is for discovering human-like driving strategies. Afterwards, I will present some experiments and results, and I will conclude the presentation with the summary and the future work. So, the problem is to discover human-like driving strategies for autonomous vehicle driving. Well, when drivers travel along a route, we actually optimize several objectives, such as traveling time, fuel consumption, maybe also some other objectives. But existing human driving models do not take these objectives into account. And the goal is to simultaneously search for human-like driving strategies and optimize also these additional objectives. In our driving simulation, we have one autonomous vehicle that is controlled by the algorithm and other vehicles, the so-called traffic vehicles, that are controlled by the simulation. We simulated also 3 routes. 2 of them were rural and 1 highway route. And at the end of the simulation, we get the traveling time, the fuel that was consumed on these routes, and the similarity with human driving. We also check the feasibility of driving. So the vehicle must not stop during the driving. This is not feasible. And there must be no collision, since there are also other vehicles on the route. The autonomous vehicle is controlled by the acceleration and the vehicle angle with respect to the route. And in addition, we control it also with the gear. Well, the gear is determined with the previous gear and the engine speed limits. We have 2 engine speed limits. So, for example, if the engine speed goes above the upper limit, the gear is shifted up. Moreover, the acceleration is limited by the vehicle constraints. So we have some maximum engine moving force that can be produced by the vehicle, and also some maximum tire braking force. So we cannot have infinite acceleration. And to calculate this constraints, we take into account several forces: the wheel friction force, the aerodynamic drag force, and the G-force. And the fuel consumption is obtained from the specific fuel consumption diagram. Regarding the traffic vehicles, so we have two lane routes. On the right lane, these traffic vehicles travel in the same direction as the autonomous vehicle, while on the left lane, well, we have 2 cases. For the rural route, they travel in the opposite direction as autonomous vehicle, while on the highway route, they travel in the same direction. And we can set for these traffic vehicles velocities and the distances to the preceding vehicle. And these change in the control action points. So at each action point, we can set a new velocity, which is achieved smoothly, and the new distance to the preceding traffic vehicle. And now I'll present the algorithm for discovering human-like driving strategies that we implemented. This is a 2-level algorithm. At the lower level, we have a set of human driving models, and these models are used to determine the control actions. While on the upper level, we search for the best input parameter values for these lower level models, and we minimize the traveling time, the fuel consumption, and while the similarity to human driving, but since we want to minimize all the objectives, we calculate the difference with respect to the human driving. As the result, we get a set of non-dominated human-like driving strategies. just a few details about the lower level algorithm. So it applies mathematical models that mimic human driving behavior. It can handle various driving operations, such as car following, free driving, so where there is no vehicle in front of the autonomous vehicle, the emergency deceleration. When there is an emergency, there is little space between the preceding vehicle and our vehicle. Then the overtaking and the lane changing. The overtaking is on the rural route, while the lane changing is on the highway. Some more details about the overtaking and the lane changing. These models actually mimic the decisions when this overtaking or lane changing should start, while the actual execution is done with Bezier curves. And we tested the algorithm on this experimental setup. So we have 3 routes, 2 rural and 1 highway. They are of 9 to 11 kilometers. On the first route, we have various velocity limits and curves and inclinations, while on the second and the third, we have a constant velocity limit and there are no curves and inclinations. On the first route, there are no vehicles, while on the second and third, there are several. And the lane changing is allowed entirely on the first route and only on the second half of the second route. Well, on the first route, there is no meaning to check this since there are no traffic vehicles to overtake. Why we used only the second half of the second route? Well, we wanted also to measure the actual car following. So we said, okay, on the first half, we will not allow to change the lane. So the person will be forced to do car following. We also recorded human drivings. We had 30 volunteers, and we obtained 2 drivings on each route. And here are the results. So these are the algorithm, the driving strategies obtained with the algorithm in the objective space. So we have 3 objectives, the traveling time, the fuel consumption, and the difference with human driving. These are just 2 views. So on the right-hand side, we can see that when we try to optimize only the traveling time or only the fuel consumption, the difference with human driving increases. While when the algorithm optimizes a good trade-off between these 2 objectives, this difference with human driving decreases. So here we can see optimization of only traveling time, here is only fuel consumption, and here is a good trade-off. And here is just an example on the last route, so this highway. And this is shown only for 2 objectives. Yes. So the traveling time and the fuel consumption, and we can see that the drivers, so these blue dots, actually are quite good at optimizing the traveling time, but not so good at optimizing the fuel consumption. So in summary, we developed a 2-level multi-objective optimization algorithm for discovering human-like driving strategies and tested on 3 routes. And this algorithm, on average, finds better driving strategies than humans, and also finds driving strategies with various trade-offs between the objectives. For future work, we would like to test additional routes and optimize specific driving operations at specific routes, since these operations are quite independent. And we will also implement additional models for handling various critical situations that are not handled well here. So, thank you.
Thank you. Questions, please?
One about
about the infeasibility. So the driving was tested, and then the results were either these objectives and also information on feasibility. Was there some measure associated with it, or was it just true false?
No, there was no measure. The driving strategies that were not feasible were just thrown away. So we didn't measure the amount of infeasibility and then put them together with other strategies.
So was the algorithm then forced to search for strategies until feasible ones were found?
Yes.
Any other question? Can you show the similarity with human driving?
This one?
It seems pretty different, right?
This is the objective space. You see, this is the measured traveling time, the fuel consumption, and the third objective. This is not the actual driving. This is the objective.
If you look at numbers, they're around 0.5, right?
Yes.
So one would be very similar. Identical.
No, 0 would be very similar.
0 would be identical?
Yes.
But okay, it doesn't change.
Doesn't change much, but yes, okay, I agree.
Okay, so it's a difference. But still it is quite different.
Well, this is also, it's a different view. You see at the left-hand side, they are between 0.3 and 0.4, this minimum.
It's realistic because, you know, when on the roads, people drive, okay? And then there is somebody, for example, like this car, and drives totally different than other humans. It would be totally asocial. I mean, other drivers would be very unhappy about it, right?
Yes, well, just one thing. We don't want to actually mimic the actual driving. Here are also some limitations, for example, for the algorithm. It cannot go above the velocity limit, while the drivers were not instructed to exactly follow the velocity limits, and so on. So these models can, in part, mimic the vehicle driving, but they cannot go, they cannot track the exact vehicle driving, human vehicle driving. So they have some limitations, but this is not to track the exact human driving, but to have different driving strategies to be then implemented inside a simulator, an actual simulator, where we can choose, okay, maybe we will choose some driving strategies that is not so like to human driving, but it will go very fast. Okay. And then another vehicle maybe will travel with a better human driving similarity, but a higher traveling time. So this is to give some trade-offs for this.
But still, making a comparison is usually under the same conditions. And if you have different conditions for two different types of, let's say, objects that you compare, it's not very usual. Usually you have the same conditions for your object that you measure. Okay, thank you very much.
Sure.
Thank you.